Okay, let's restart. Before fourth lecture, I'll talk about the next lecture. Uh, Today is April 22nd. Uh, so next week, April 29th, will be a holiday for Showa Day. Uh, and the following week, May 6th, will also be holiday. Substituting holiday for a greenery day. Therefore, our next class will be on May 13th. So please note that this is quite far in the future, so please keep this in mind when planning. Okay. Okay, I would like to start the fourth lecture now. Today, I will introduce rate regulation and last regulation, which are famous regularization methods. First, let's review what we learned last time. Let's say we have n sets of data such as the set with xy1, x12, x1p, y1, x21, x22, x2p, y2, and so on. For these data, we want to find beta 0, beta 1, beta p that can approximate that data as shown in this equation. This is what multiply regression is about. The algorithm we got from the least square method was this one. We define X as a matrix with the explanatory variable arranged in column with a column of ones added at the beginning, and Y as the vector of the objective variables arranged like this. By calculating in this way, we can find the parameters of linear regression. However, we need to check the rank to see if tx real if xtx really has an inverse matrix. Rank x equals p plus 1, it has an inverse matrix. But when it is less than p plus 1, it is known that xtx does not have inverse matrix. XTX having XTX having inverse matrix that is being regular is the same as its determinant not being zero. Since data contains noise, the determinant is rarely exactly zero. So the possibility of xtx not being regular is low. But when the value of the determinant is small, problems can happen. For example, the inverse of the two-dimensional matrix is given like this. The AD minus BC here is the determinant of the original matrix. So when the determinant is small, we are doing something close to the division by zero. When we divide by small number, the result can become very large. When does the determinant become small? One case is when n is less than p plus 1, meaning there are fewer data points than explanatory variables. Also, when there is a strong correlation between the columns of the matrix, the determinant becomes small. For example, if we have column of 1, 2, And another column of 1, 2.01, the determinant would be 2.01 minus 2. So the determinant of this is 0.01. What does it mean when there is a strong correlation between the columns of the matrix? It means there is a strong correlation between the explanatory variables. Does this really happen? Actually, it's common problem in real situation. For example, let's say we want to create a model to estimate house price. Using explanatory variables such as lot area, floor area, age, and distance from the nearest station. Let's consider fictional data. The expected relationship might be plus is floor area times 10 minus age 2 times 10 minus distance from station times 15, while price is minus lot area times 10 plus floor area times 25 minus age times 10 minus distance from station times 15 would give the same prices. This equation fits the data, but it strangely suggests the largest lot area leads to lower prices. Something seems wrong. Uh, the trick is that there is a strong correlation between lot area and floor area. Specifically, the floor area. Uh, so the lot area is the 1.5 times. The floor area is 1.5 times the lot inverse. Anyway, okay. So this kind of strong correlation between explanatory variable is common. For example, in surveys, if two questions are similar, they will get a similar answer. Just by including such data, we end up with two explanatory variables that have a high coefficient correlation. When there is a combination of explanatory variable with high correlation coefficient, it is said that multicollinearity. So how do we fix this? Looking back at the original page, we can see that dividing by the small number can make the numbers becomes large. The problem is that the coefficient beta 1 to beta p may be large. So the idea is to present these coefficients from becoming too large. We also want to avoid the situation where the determinant value is small. This led to the development of ridge regression. Originally, the least squares method was a problem of minimizing the square or the sum of square like this. Ridge regression adds the sum of square of parameter to this function that we want to minimize. Ridge regression asks you to find the parameter to give the minimum value for the modified problem. In other words, ridge regression tries to make the sum of square of the coefficients small as well. You can see that the summation here starts from 1. So the constant from term beta 0 is not included. It is common not to include the constant term in the sum of square. The idea is that we only want to make the coefficient of this part, the coefficient of the explanatory variable. That is the parameters small. At the beginning of this equation, there is a factor of 1 over 2n. By multiplying by a constant does not change the parameter that minimizing the function. So 1 over 2n is just there to make the calculation easier. Also, regression has this parameter lambda. If lambda is set to 0, it becomes just originally least square method. If lambda is taken to very large, the first part of the equation, which represents how well the model fits the data, becomes relatively small. So it becomes a problem of minimizing only the sum of square of the parameter. When does this sum alone become minimal? It happens when all parameters are zero. So when a large is zero, it is just the original least square method. And as method gets larger, the values of beta are designed to become smaller. Now let's calculate when beta minimizes this function. Let's work out the partial derivative. Okay. Mm, L can be written like this. When we partially differentiate L with respect to beta 0 to beta p, we get this result. Beta 0 appears, so beta 0 appears only here. So the partial derivative with respect to beta 1 is the same as in the ordinary least square method for the first time. But because of the regularization term, we get to lambda beta 1, so this term, lambda beta 1 from here. Lambda beta 1 from here. So partial derivative with respect to beta p also takes a similar form. If we use the mean of each exponential variable and the mean of the objective variable, when the partial derivative with respect to beta 0 equals 0, this becomes the 0. When we expand it, this part becomes beta 0. So let's try. Okay. So the partial derivative of with respect to beta 0 is equivalent to minus n 1 over n and yi minus beta 0 hat P beta J hot Xij equal to 0. So, when we expand it, minus n plus, uh, so this part becomes beta 0 because we add beta 0 n times and divide by n. And so here we can exchange the order of summation for I and j. So first, well, sorry, this part. So this part is so this part we can exchange the order of summation for I and j. So P and j hot and xij. Yes. So when we rewrite the order, it becomes like this. So this part becomes the mean of the j's explanatory variable. So x I no j. So this part becomes the mean of the objective variable. So y bar. Therefore, we maintain minus 5 bar plus beta 0. I forgot to hat. And j2 1 beta j hot xj bar or 0. So using the means, it becomes like 0, like this. So this means that beta 0 can be written using beta 1 through beta p. Next, we need to find beta through beta p hat, beta p. Let k be any number from 1 to p. For the partial derivative with respect to beta k to be 0 using what we calculated earlier, this must be 0. Okay, let's calculate. Mm, By a yi minus beta 0 hot. Here, so here, based on the relationship we found earlier, beta zero hat can be written like this: y bar minus p 1 beta j hat x bar. So, minus n over 1 x I k y bar minus pj 1 hat. Okay, so let's define variable with their means subtracted using symbol with tilde. So y tilde, so xij tilde. Then this part becomes y tilde. This part becomes x tilde ij. Here, this can be broken down like this: x tilde ik plus xk. So we obtain minus. y tilde minus beta j hat x tilde ij 0. So here, minus n over nx だけ p beta j hat. So this part is equal to n y tilde plus nx tilde x over k r j beta j hat. Okay, so but see here, yi tilde is the original yi minus its mean. Its average is 0. So this part is 0. Similarly, x tilde ij is xij minus its mean x bar xj. So its average is 0, also 0. Therefore, this term is 0. So the terms that will be to contribute here disappear, and we get Mhm. No, 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 no. Let's copy. Hey, so we obtain. Oh, I forgot. Well, I forgot this part. Oh, I forgot. I forgot. Yes. So we obtain these systems. So let's define the matrix X tilde and the vector Y tilde and the beta hat minus zero like this. X tilde is arranged the variables where each row corresponds to one data. So X tilde is n times P matrix. The centered objective variable that is with the mean subtracted is y tilde. The arranged variable values of beta 1 hat through beta p hat are beta hat minus 0. And then, so then, first term, so this term is the first term. This part. The first term in the previous system of the equations correspond to the ith element of y children. So this part is correspond to y children minus x children minus 0. And this part is correspond to x children t yi. So here extruder I1 can be seen as I component of the transpose of extruder. So this correspond to this equation. And when we correct the term with beta hat minus 0, we get extruder t extruder plus n lambda I. Uh, beta hat minus 0 equal x tilde t y tilde. When x tilde tx plus n lambda has an inverse matrix, we find uh, that L is minimized by beta hat minus 0 equal x tilde t x tilde plus n lambda inverse x tilde t y tilde. In the ordinary least square method from before, we don't have the n lambda term. In fact, if lambda is positive, then x tilde t x tilde plus n lambda I is always regular, which is why this is called regularization. Adding the sum of square of coefficients this term to the function to be minimized is also called ridge regularization or L2 regularization. Because this part is called L2 norm. Okay, okay, let's take a break. Okay, sure. Okay, let's restart. Let's prove the x tilde t plus n lambda I is always regular. First, let's look at the properties x tilde t x tilde. Uh, Specifically, we will show that the eigenvalues are non-negative. According to the reference book 1, proposition 9, it's known that a symmetric matrix can be diagonalized using appropriate orthogonal matrix P to calculate over minus 1. P is resulting in diagonal matrix with eigenvalues on the diagonal. This is what we call diagonalization. Symmetric matrix means for all components uh, in row J and column I, in other words, sorry, the component in row I and column J is the same as the component in row J and column I. In other words, it remains the same when transposed. To check if x tilde t x tilde t x tilde is a symmetric matrix, we can look at its ij component, this. It becomes a GI component, so we know that it's a symmetric matrix. Therefore, by this proposition, there exists orthogonal matrix P, and we can diagonalize it using P. Here, mu1 to mu p are the eigenvalues of x tilde t x tilde. Since P is orthogonal matrix, its inverse is equal to its transpose. So the previous P inverse, blah blah, can be rewritten as x tilde P transpose x tilde P. If we take any vector beta, multiply it from the right and multiply beta t, so the previous this one can be written as sorry. So since it's a quadratic form, it corresponds to this one. Since the square of the norm is always non-negative, we know this is non-negative. So, since this is non-negative for all beta, so all eigenvalues are also non-negative. Finally, we begin the proof x tilde t x tilde plus n lambda I is always regular. Uh, since we have that, we take determinant, we obtain this. Here, so this part is equal to determinant P inverse determinant x tilde t x tilde plus n lambda I determinant P. And this part is equal to inverse of determinant P. So this part, so they cancel out. So this equal to this one. So on the other hand, the corresponding part is this one. So this determinant is mu1 plus n lambda times blah 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 times mu p plus n lambda. So when lambda is positive for all j, mu j plus n lambda is positive. So the determinant is positive. Therefore, x tilde t x tilde plus n lambda I is regular. So therefore, since the determinant is greater than 0, this means while x tilde t x tilde might not be regular, this becomes regular. This is why it's called regularization. Something that wasn't regular becomes regular. So after all discussion, we call use what we calculate to determine the parameter for ridge regression, like that. Okay. Okay, as I mentioned, okay, skip. As I mentioned earlier, I gave example of when the determinant value becomes small. One was when there is a strong correlation between the column of the matrix, which we solved with ridge regression. The other case was when n is smaller than p plus 1, meaning when there are fewer data points that explain a variable. You might wonder if such situation actually occur, but when dealing with big data, the number of explanatory variables can become very large. This is a problem that has arisen in recent years due to the development of the storage media and measurement technology. For example, in the field of biology, the expression levels of tens of thousands of genes sometimes use explanatory variables. Genome sequencing has only become possible recently. Genomic information contains an enormous amount of data. This becomes one data point. There is a lot of information in just one data point. It is important to find a small number of truly necessary explanatory variables from a large number of explanatory variables. Whereas the genome is very long data. If you ask which part affects cancer, for instance, not all parts have an influence. Only a very small portion does. So the truly necessary parts are few in number. To obtain a highly interpretable model, it's necessary to narrow down to a small number of important explanatory variables. The number of components of beta is called L0 norm, and ideally, we would want to consider minimization problem where number of the non-zero component is less than or equal to some number. However, LZ is mathematically difficult to handle. It's not even a norm in mathematical sense. Since LZ norm is difficult to handle, the L1 is often used instead. The L1 norm is the sum of absolute values of each values. Earlier, we add the sum of square of a parameter to the minimized problem, but we can also add the sum of absolute value to the problem. Interestingly, using this approach causes many coefficients to shrink to zero. This is because as lambda get larger, the problem becomes more about minimizing this part. So this part. In that case, optimal situation would be when all parameters are zero. So large lambda is closer each coefficient gets to zero. This is also a form of regularization. So this method can also be solved when n is less than p plus 1. This method of adding the L1 norm is called lasso. Uh, In each regularization, we added the square of parameter, but in Lasso, we changed this part to sum of absolute value of parameters. How do we calculate this? For the least square method and rigid regression, we calculated the partial derivative and found the imbalance matrix, but this approach doesn't work well for large regression. There is no practical method to obtain the solution in one step. Instead, we consider a method to gradually approach the solution. Let's consider the coordinate descent method. Uh, we fix beta 2, beta p, beta 2, 3, beta p, and calculate beta 1 such that error is minimized. Next, we fix beta 1 and beta 3 through beta p and update beta 2 to minimize error. And so on. Finally, we update beta p and then start again with beta 1, repeating this process. This is coordinate descent method. We gradually approach the solution and stop when the amount of change becomes very small. Once beta 1 through beta p are determined, we can calculate beta 0 in the same way as before, so rigid regularization. As before, the absolute value of beta 0 doesn't appear in the last objective function. So beta 0 can be calculated using beta 1 through beta p just like before. To minimize error, we need to differentiate with respect to beta 1, but then we need to differentiate the absolute value of beta 1. And the question is how to do that? When we consider the derivative of absolute value function when x is greater than 0, the absolute value of x equals x. The derivative is 1. In the other words, the slope is 1. When x is less than 0, this becomes minus 1. The slope is minus 1. So at x equals 0, the right hand limit is 1. The left hand limit is minus 1. These limits are different. We cannot differentiate at the origin. Why did we want to differentiate in the first place? Because our differentiable convex function takes its minimum value at the point where the derivative is 0. For convex functions, the derivative corresponds to the slope of a tangent line that touches the graph from below. For a differential convex function f, a slope that is tangent to the graph corresponds to this. In other words, if you draw a tangent line, all other parts of the graph will be above the tangent line. So we will extend this concept as long as the slope satisfies this condition. So this one. As long as the slope satisfies this condition, we can interpret it as something like a derivative. This L is said to be included in the subdifferential. More precisely, the subdifferential of z at x equal a is defined as this set. You can think of it as the correction of the slope that touches the graph from below. Let's see what the subdifferential of gx equals absolute value of x at x equals 0. From the definition, we need to find L that satisfies this inequality. And this turns out to be any number between minus 1 to 1. So please check here later. On the other hand, for a differentiable function, if we draw a graph, it becomes easier to understand the graph. So like that. Like that. For example, uh, if we consider a line with slope 1 over 2, this line is completely below the absolute value function. So according to our earlier reasoning, 1 over 2 is including in the subdifferential. Any line passing through the origin with a slope between minus 1 to 1 lies entirely below this graph. So it's in the subdifferential. For a differential function, the subdifferential at x is a is from the previous proposition, this one. Only the derivative itself. We introduced the concept of the subdifferential, but what make it useful is that we can state something similar to proposition 1 in terms of subdifferential. When the subdifferential of convex function at x equals a contains 0, the value at any other point is greater than or equal to the value at a. In other words, as long as the subdifferential contains 0, the function takes its minimum value there. In our earlier example of the absolute value function, the subdifferential So here like that. Uh, x equals 0 was a range from minus 1 to 1. This interval contains 0. The value at any other point is so from position 4, g takes its minimum value at x equals 0. Indeed, looking at the graph, we can confirm this. The amazing thing is that we can find the minimum value even when the function is not differentiable. Now let's tackle loss regression. When we partially differentiate L with respect to beta k for beta k greater than 0, uh, the first part, the calculation is the same as what we did the ridge regression. So it looks like this. However, when we differentiate the absolute value, we get lambda. When beta k is less than 0, we get minus lambda. So the differential of L with respect to beta k at beta k, when all other beta values are fixed, looks like this. This follows the same reasoning as with the absolute value function earlier. To simplify this expression, let's define Rk, Sk. We split the sum into the part, this part, y tilde I minus the sum of all this part is minus beta k x tilde I k minus j not k beta j x tilde I j. Then, so this part is equal to Rik. This part is correspond to Sk. So this allow us to rewrite the expression. And if we define this part, if we define Sk as the sum, so yes, so we obtain. Finally, we obtain this part. Uh, Here, sigma k square is the variance of the case explanatory variable. So, the subdifferential of L uh, when beta k is greater than 0 is this, beta k is less than 0 like this, beta k is 0 like this. For 0 to be included in this, minus sk plus lambda must be negative. In this case, this becomes 0 is equivalent to this. So other part is same story. In summary, when sk is less than minus lambda, sigma k square beta k equals sk plus lambda. When sk is greater than lambda, it's equal to sk minus lambda. So other case is equal to 0. This can be written using what we call a soft threshold function. If you didn't quite follow, the main point is that if you have the value of sk and sigma k square, you can determine beta k. In Python, we can write this using if statement. However, when performing calculation on a computer, it's better to avoid conditional branches. This alternative way of writing it is actually faster. You can check this for yourselves. The threshold, soft threshold function can be written like this. The algorithm for loss regression looks like this. We calculate the mean, center the data to get x children and y children. Once we have these, we can calculate R and S. And then use the soft threshold function to find beta j. We compute this by moving j from 1 to p and check how much beta has changed from its original value. When these almost no change, we interpret this as being close to the solution and end the process. There is some mistakes. This part should be beta, and this part is k. Okay, and I forgot sigma k square. This is correct. I will upload these slides after lecture. Okay. Okay, so let's look at the specific calculation. This graph shows how the parameter change as lambda variables. For this example, we consider data with 100 samples and 20 parameters. Most parameters are 0, with beta 1 equal to R, beta 2 equal to minus 1.5, beta 3 equal to 2. After calculating the objective value, adding noise, and applying loss regression, we can see that beta 1 has largest absolute value. So we can infer the first explanatory variable has the strongest influence. Let's summarize what we've learned. Linear regression is the most basic method that estimates model coefficients by minimizing the sum of squared errors. It's simple, making it easy to interpret, understanding, and implement. However, it may not work well when there is much collinearity or where there are many explanatory variables compared to the number of data points. Ridge regression addresses the much collinearity problem. This method is the sum of squares of coefficients of the objective function of the least square method. This allows us to get stable result even when there are many explanatory variables. For cases with many explanatory For cases where with many explanatory variables, loss regression is a natural choice. It adds the sum of absolute values of the coefficients to the objective function of the least square method. This enables a variable selection. Both ridge and loss regression requires choosing lambda, which you need to decide yourself. Since manually determining it for each dataset is difficult and time consuming, and it's hard to know what a good parameter is, cross-validation is often used. Also, rich regression doesn't have the feature of narrowing down explanatory variables, and last regression doesn't necessarily avoid the multiple collinearity. So there is also elastic net, yeah, like that. Which combine both approach. It has both the sum of square and the sum of absolute values. So if we want to create a model that's strong against multicollinearity like ridge regression while also excluding unnecessary coefficients like loss regression, elastic net is a viable option. Okay, now let's move on the code. Okay, let's explain the code. We will use 04 regularization. This one. Okay, so let's execute. Okay. We are waiting. Okay. So we prepare the library to be used. Rich regression is so the rich regression function is defined here. So it's written in slides. Okay, so let's now apply the rich regression to real data to see how it works. First, we will create data with strong multicollinearity and verify its effect. First, we generate the data. We prepare and is 10 data points. We set two parameters. The beta is 1 to 3. We generate explanatory variable x1 randomly and set x2 as twice x1. The object variable y is calculated as beta 0 plus beta 1 x1 plus beta 2 x2. Okay. We create x by combining x1 and x2. Now that we have our explanatory and the objective variables, we calculate the coefficient using a regularization parameter of 0.1 here. For data with strong match quality like this, ordinary least squares would result in very unstable calculations and poor estimation. However, rich regression, oh, oh, ah, sorry, I forgot this one. Okay, like this. By adding regularization term, rich regression can handle the calculation without difficulty. Now let's try the case with explained variable without much collinearity. In this case, ridge regression with regularization parameter set 0 here should give the same result as simple multiple regression using the least square method. When we check the result, we find the intercept obtained from ordinary multiple regression is approximately 0.94. And the rich regression gives the same value. The coefficient for the experimental variables are the same, also exactly the same, and this here. Confirming that related regression with regularization parameter of 0 gives exactly the same result as the least square method. Now let's look on the last regression. Here we prepare speed. This is last regression function. Okay. Yes, this is an example of applying last regression. This part is written in the slides. Looking at in actual example, we set true parameter beta as 3 minus 1.5 to 0, 0, 0. With zeros following the first three variables. Generate x randomly and set y as a product of x and beta plus noise. When we apply last regression with a regularization parameter of 0.1 to this data, we obtain variables remarkable close to this part. Close to the original 3 minus 1.5 2, 0, 0, 0. This suggests that the first experimentally variable has the greatest influence. Regarding the choice of lambda, trying the various values and plotting the coefficient against lambda shows the coefficient tends to 0. Lambda is increased. When lambda is small, many parameters have non-zero values. But the order of magnitude uh, of the coefficient absolute values doesn't change. This allows us to identify which independent variables have the greatest influence. That conclude. So I wasn't able to finish explaining all codes today, so I will go over it during our review in the next class. That concludes. Anyway, that concludes the explanation of last regression implementation and uses example. So please work on the in-class assignment, report from the last page. Okay, let's go. Okay, so please work on the in-class assignment from the last page here. Some people only submitted one of the assignment last week, but please make sure to submit both. For this time, please submit of the fourth assignment and third assignment. So please submit both this and this. Okay, that's all.